Hello students. Have you ever been on a smooth ride where a car steadily picks up speed? Or maybe you've watched an object fall from a height like an apple dropping from a tree. In both these cases, the body moves with a constant acceleration. And today, we're going to explore the exact equations that describe such motion. When a body accelerates uniformly, that means it gains or loses speed at a constant rate. There are 3 golden equations of motion that connect 5 essential quantities. These equations are the keys to solving all uniformly accelerated motion problems, whether it's a spacecraft launching or a ball dropping. Now let's begin with the first equation, v equals u plus a into t. Here's the idea. Acceleration is the rate of change of velocity over time. That means acceleration equals open bracket final velocity minus initial velocity close bracket divided by time, or simply a equals open bracket v minus u close bracket divided by t. Rearranging this, we get v equals u plus a into t. This tells us how the velocity of a body changes after time t. If it's accelerating at a constant rate, as you can see in the velocity time graph in figure 2.45, the velocity increases in a straight line starting from point O with initial velocity u and reaching final velocity v at point C. Just like how a car goes from 0 to 20 meters per second in 5 seconds with steady acceleration, this equation tells you how fast it ends up going. Let's move on to the second equation, and this time we're going to use geometry. We calculate distance by finding the area under the velocity time graph. Look at the trapezium formed under the graph. It consists of a rectangle and a triangle. So, displacement S equals area of rectangle OAED plus area of triangle ABE. That becomes S equals U into T plus 1 by 2 into open bracket V minus U close bracket into T. Now using v equals u plus at and simplifying, we get s equals u into t plus 1 by 2 at squared. So the second equation is s equals ut plus half at squared. Pretty neat, right? A simple graph gives us a powerful formula. There's another way to arrive at the same second equation using average velocity. Average velocity is just the mean of the starting and ending velocities. So, average velocity equals open bracket u plus v close bracket divided by 2. Then displacement s equals average velocity into time. Substitute for v again as u plus at. Simplify and we land again on s equals ut plus half at squared. This method is especially helpful when working with word problems or real-life examples like trains picking up speed gradually. Now let's say we want to find the final velocity, but we don't know the time. What do? That's where the third equation comes in. Starting with the same idea, s equals average velocity into time, and t equals open bracket v minus u close bracket divided by a. Plug this into our expression for s and simplify. We eventually get v squared equals u squared plus 2as. This is the third and final equation of motion. And as you can see, no time involved. This equation is useful when time isn't given, like finding the speed of a ball just before it hits the ground after falling a certain distance. Let's now explore how these equations adjust in special cases, like when the motion starts from rest or when the body slows down. Case 1. When the body starts from rest. That means u equals 0. Then the equations simplify to v equals a into t, s equals 1 by 2 at squared, v squared equals 2as. Case 2. When the body is under retardation. Here acceleration is negative, so the equations become v equals u minus at, s equals ut minus half at squared. V squared equals u squared minus 2as. Understanding these cases helps apply the right form in various situations, like braking cars or upward motion. All right, learners, let's quickly revise everything we've discovered today. When a body moves with uniform acceleration, we use first equation, v equals u plus a into t, tells how velocity changes over time. Second equation, s equals u into t plus 1 by 2 at squared, gives the distance covered. Third equation, v squared equals u squared plus 2as, relates velocity and distance, no time needed. You've also seen how these equations come from simple geometry and logic, using graphs and average speed. These aren't just formulas, they're tools to understand how things move all around us, from free-falling objects to vehicles to even planetary motion. I hope now you feel confident about solving motion problems using these three equations. In our next topic, we'll apply them to real-world examples and challenges. Until then, keep exploring the physics behind every motion around you.